Hello everyone and welcome to a new stream. How are you doing, guys? I'm doing good. So today is the 5th day of learning about matrices. Yesterday I managed to stream about OpenGL, but I didn't stream about developing the form builder. I don't know why, but for some reason I I'm I always fall asleep, or I have to. I don't know. I I felt physically weak and I couldn't do it. But someday I will get used to this, right? So what we learned the last time is how to calculate the how to calculate uh, how to solve linear equations using matrices, right? We have everything here. Look at this. Apparently the row echelon form is always strictly to the right of the pivot of the row above it. So the one thing is not that true, but to achieve that we must convert everything to 1 so we can add -1, right? Using the -1 trick that is explained. No, it's not explained here. It's explained right here. This isn't the echelon form. No, this isn't, because we have a missing one here. So we learned about this thing, right? We calculate the inverse of a matrix. This is pretty interesting, right? We have this data, right? Then we write the augmented matrix with an identity matrix. Then we have to do some transformation. We have to use Gauss elimination, and then we have to bring it to the row echelon form, right? After we did that, we are ready to go. We have to watch more about it. So I will. Okay. The last stream suddenly interrupted. I apologize for that, but we are gonna cover this topic later. But for now, let's search how. Let's look more about in calculating the inverse of a matrix. So this is pretty easy, right? Well, let's. Oh, this also covers 4x4 matrix. Let's try. Let's watch this. Okay, that seems interesting. Cannot. I have to refresh the page because.
Although a matrix is different from a function, when denoting the inverse of a matrix, we will use similar notation as we did for functions, where the inverse of matrix A will be A with a -1 in superscript, just like a function f and its inverse.
Yeah,
we must realize that this is not an exponent. A inverse does not mean the reciprocal of A, or 1 over A, because there is no such thing as matrix division. But an inverse matrix is similar to the reciprocal of a number in another way. We can recall that a number times its reciprocal equals 1. Similarly, a matrix times its inverse, or the inverse times the original matrix, will yield an identity matrix, a square matrix with all zeros except ones across its main diagonal, which is kind of like the number 1 in matrix form. So in that sense, there is a correlation. Now, we know how to perform matrix multiplication. So how exactly can we structure an inverse matrix so as to get an identity matrix when multiplying by the original matrix? Let's start with a simple 2x2 matrix with entries A, B, C, and D. The inverse of this matrix will be 1 over the determinant of this matrix times this new matrix with entries D, -B, -C, A.
Yeah, that's pretty much how it works for the determinants, right? I mean, for 2x2 matrix, we calculate the determinant and then we multiply it by 1 over this. We also have to, to reverse this part, and then we have to switch A with D, and then we have to put the other diagonal negative, right? We have to multiply by -1.
So A and D have swapped positions. B and C have gone from positive to negative, and the resulting matrix is being divided by the determinant of the original matrix. To see why this is the case, let's multiply this inverse in this general form by the original matrix. First, let's just generate the 2x2 matrix that is the product of these two without worrying about this determinant. For the first entry, we get DA plus -BC, or keeping everything in alphabetical order and simplifying the sign, AD minus BC. For the second entry, we get BD minus BD. Then moving down a row, we get -AC plus AC. And for the last entry, -BC plus AD.
Man, that makes sense. Like, these two already cancel out, and then we simply put 1 divided by this, and we basically have 1.
Or AD minus BC. The upper right and lower left terms clearly become 0, leaving us with this. Now we can divide by the determinant like we originally said, meaning each entry in the matrix will be divided by AD minus BC. AD minus BC divided by AD minus BC is 1, and the zeros don't change. So we are left with this 2 by 2 identity matrix, just like we expected. So that's how you get the inverse of a 2 by 2 matrix. You swap A and D, change the sign on B and C, and divide by the determinant of the original matrix. Let's try a concrete example to make sure we have this. How about a matrix with entries 4, 3, 3, 2? To get the inverse, we find 1 over the determinant, and the determinant is 8 minus 9. So here we have 1 over negative 1, and after that comes the 2 by 2 matrix with these two entries swapped and the signs of these two inverted. That gives us 2, negative 3, 4. Incorporating this negative 1 out here is easy. That just gives us negative 2, 3, 3, negative 4. And that is the inverse of this original matrix. Just to make sure this worked, let's multiply them together and see what we get. We do get the identity matrix, so we know our answer was correct. So what do we need inverse matrices for? Well, as we said earlier, there is no such thing as matrix division, so we can use this technique to solve equations with matrices where division would be necessary from an algebraic standpoint. If we have matrices X, A, and B, where X times A equals B, and we want to solve for X, we can't divide both sides by matrix A. Instead, we can multiply both sides by A inverse. On the left side of the equation, A times A inverse will give us the identity matrix, which we can essentially treat like the number 1 and just get rid of it. And on the right side of the equation, we have a product of two matrices that we can compute, which will be equal to X. Of course, this assumes that the dimensions of these matrices are such that the product can be calculated. Otherwise, this will not work. Don't forget that matrix multiplication is not commutative. So wherever we place A inverse on one side, we have to place it the same way on the other side. So in this case, as the rightmost entry on each side. If the original equation was A times X equals B, we would have to place A inverse all the way on the left, because A inverse times A should also equal the identity matrix, in which case the right side must be A inverse times B and not B times A inverse.
Okay, that can be confusing, right? Yeah, we have to look the position of the X.
If the original equation was A times X equals B, we would have to place A inverse all the way on the left, because A inverse times A should also equal the identity matrix, in which case the right side must be A inverse times B and not B times A inverse. In addition, when taking the inverse of a product of matrices, like the quantity B times A inverse, we get A inverse times B inverse in that order. We should also note that not every matrix will have an inverse matrix. If a matrix has a determinant that is equal to 0, its inverse will involve dividing by 0, which is undefined, and that matrix will therefore not have an inverse. Such a matrix is called a singular matrix.
The determinant is A times D minus C times D, right? I mean B.
Lastly, you may be wondering how we can find the inverse of any matrix other than a 2 by 2 matrix. Let's look at a 3 by 3 matrix and see how this would work. To find the inverse of this, we will first find something called the matrix of minors. This will be a new 3 by 3 matrix, and each entry will be a particular determinant. For the first entry, we locate the corresponding entry in the original matrix, and we block out its row and column. There is a 2 by 2 array of numbers left, and we find its determinant. That determinant will become this first entry in the matrix of minors. Then for the second entry, again we go to the corresponding entry in the original matrix, block out its row and column, and find the determinant of what is left. We continue doing this for every single entry until we have completed our matrix of minors. Unfortunately, that was just step 1. Now for step 2, we use our matrix of minors to generate a matrix of cofactors. This isn't too hard. We just have to apply a checkerboard of plus and minuses to get the right sign on each term. The corner entries and the central entry will remain as they are, and the other 4 entries will have their signs inverted. Then step 3 is to find the adjugate, or the adjoint. This involves reflecting all the entries across the diagonal. The diagonal stays as it is, but the other terms are reflected. So these 2 swap, these 2 corners swap, and these 2 swap. Finally, the last step involves dividing by the determinant of the whole original 3 by 3 matrix, which won't seem so hard after doing that whole business with the matrix of minors. We just have this first entry times the determinant of this 2 by 2 matrix, minus the second entry times the determinant of this 2 by 2 matrix, plus the third entry times the determinant of this 2 by 2 matrix. Whatever we get, we divide the last matrix we had by this value, meaning we divide every entry in the matrix by that value. And that's what we are left with for the inverse of the original 3 by 3 matrix.
So there are multiple ways to find the inverse of a matrix.
So to summarize the 4 steps we just took, first we found the matrix of minors going 1 entry at a time. Then we applied the checkerboard pattern of signs to find the matrix of cofactors. Then we transposed all entries across the diagonal to get the adjugate. And lastly, we divided by the determinant of the original matrix to get the inverse matrix. This is essentially the same algorithm as we used for a 2 by 2 matrix, just many more steps to achieve the same result. So as we can see, even with just a 3 by 3 matrix, finding the inverse becomes rather laborious. If we were to extend this to a 4 by 4 matrix, it wouldn't really be any harder. We would just end up with an absurd amount of steps to follow. For this reason, inverses of larger matrices are usually found using some kind of matrix calculator to avoid doing pages of arithmetic. So that's what we need to know about inverse matrices. Now that we have covered the basics about matrices, their operations, determinants, and inverses, we have many of the important algorithms out of the way, and we are ready to examine some of the more abstract ideas in linear algebra. But before we move forward, let's check comprehension.
That's cool. Oh, we can do that. So there are some steps to memorize, right? Yeah, this is what I say. Like, there we can use the goes to each long form method, and we can achieve the same result. And that would be easier, right? So we have these 2 ways. I would implement the first one, right? So let's try how to do that. So let's repeat the steps. Let's try to write a C algorithm for that. By the way, I didn't the last time I also didn't manage to do this. To do these two to complete these two functions. But I wouldn't focus on that. That's because doing on paper is way easier. Like it's like you see numbers and then you know where to swap rows or add add things together, right? On this side, by the way, it's much harder because you have to check, you have to use, you have to write the logic that does this. Honestly, I wouldn't waste time for this. But if I have to do that, yeah, well, I have to, I will have to implement someday. But for now, I won't implement this algorithm. I already tried and I wasted hours. And we completed one of the steps, but this is like a more visual, a more visual procedure. So we don't actually have this part right here. Like we don't really need that, but we will definitely implement this, right? Also, if the determinant of A is 0, this is a singular matrix. Okay. So let's try to calculate the inverse of this matrix.
Lastly, you may be wondering how we can find the inverse of any matrix other than a 2 by 2 matrix. Let's look at a 3 by 3 matrix and see how this would work. To find the inverse of this, we will first find something called the matrix of minors. This will be a new 3 by 3 matrix, and each entry will be a particular determinant.
So we have to calculate each determinant of this submatrix, right? So this part cancel out, and then we have this, the determinant of this matrix, and then we have to divide each element for the whole determinant, right?
For the first entry, we locate the corresponding entry in the original matrix, and we block out its row and column. There is a 2 by 2 array of numbers left, and we find its determinant. That determinant will become this first entry in the matrix of minors. Then for the second entry, again we go to the corresponding entry in the original matrix, block out its row and column, and find the determinant of what is left. We continue doing this for every single entry until we have completed our matrix of minors. Unfortunately, that was just step 1. Now for step 2, we use our matrix of minors to generate a matrix of cofactors. This isn't too hard. We just have to apply a checkerboard of plus and minuses to get the right sign on each term. The corner entries and the central entry will remain as they are, and the other 4 entries will have their signs inverted. Then step 3 is to find the adjugate, or the adjoint. This involves reflecting all the entries across the diagonal. The diagonal stays as it is, but the other terms are reflected. So these 2 swap, these 2 corners swap, and these 2 swap. Finally, the last step involves dividing by the determinant of the whole original 3x3 matrix, which won't seem so hard after doing that whole business with the matrix of minors. We just have this first entry times the determinant of this 2x2 matrix, minus the second entry times the determinant of this 2x2 matrix, plus the third entry times the determinant of this 2x2 matrix.
Right.
Whatever we get, we divide the last matrix we had by this value, meaning we divide every entry in the matrix by that value. And that's what we are left with for the inverse of the original 3x3 matrix. So to summarize the 4 steps we just took, first we found the matrix of minors going 1 entry at a time. Then we applied the checkerboard pattern of signs to find the matrix of cofactors. Then we transposed all entries across the diagonal to get the adjugate. And lastly, we divided by the determinant of the original matrix to get the inverse matrix.
Yeah. Right. So we have to implement this right here if we want to, if we want to implement this right here, right? Right now, what we have to do is you simply have to, let's see, we get a new matrix, right? And then we have the matrix of minors. So I will call it minors matrix, right? Then we pass the matrix like that, right? Is this the correct term? So matrix of minors. It is the determinant of this part right here. Let's check what a minor is. In linear algebra, a minor of a matrix A is the determinant of some smaller square matrix, generated from A by removing one or more of its rows and columns. Okay, that's interesting. Uh, we always need the square matrix, right? Like this applies only to square matrix. So yeah, we should do that, right? So let's. I will create another function that does this. So I call it. This will return. This will return a scalar value, and then I will call this minor, and then we pass the matrix. Then we pass I and j, like that. So what we have to do is we just have to exclude this element, and then we calculate the determinant with this matrix, right? Whoa, what the hell? What's going on? Bro, oh my god. Fucking hate Windows. But before doing this, I will create another function, right? Probably it's not that convenient. So the determinant, this is the algorithm to calculate the determinant, right? So let's implement these two functions. And this will be important too for our matrices, right? For for to get the process, like to implement the invert matrix function. I think in this case it would be more efficient than using these two, right? Literally. But we shouldn't forget the other two ways to do that. Then we have the cofactor, right? What is this? We have the Laplace expansion. Ah, okay, I know what it is. So this -1 is like, how can I say it? That is is multiplied by I plus j times, right? And this will give us will switch between positive and negative numbers, and then it is multiplied by the entry point, right? This is the minor of b, which is the determinant for each point, right? And this is the Laplace expansion. An algorithm process that we can just include this here in C, right? We won't do this. We will just multiply this by I plus j if this is 0 or 1. I mean the module of this I plus j. We will use a similar formula for this. So where oh god, I lost. So we have the Laplace formula, right? This is applied right here to get the cofactors. The cofactor is simply the signs applied to each entry point, right? We don't need a new function for this. Like, I don't think this is that important. But it is enough to know how this works. That this formula exists and everything. So to calculate the inverse of a matrix, right? We have this. We have some steps. And this is, first thing is find the minors. So you find the minors and then you put them in the matrix. And yeah, after you find the minors, after you found all the minors, and put them in these shells, you apply the cofactor. Then you have to divide them, right? You have to divide each cofactorate minor by the determinant of the original matrix, right? Oh, before that we have to reflect this matrix, right? But we can implement this function that gives us the actual thing, right? So we have this part. Let's implement this function. So diagonal reflect. Then we pass the matrix, right? Then what we have to do is, should we allocate memory for this? We simply have to swap elements, but for now we won't allocate any memory. This will return the same matrix you passed right here. No allocation is performed. This too will allocate memory. This will create a new matrix. This will generate a new matrix. This, of course, will allocate memory. And this is really obvious. So this also will allocate memory. So let's implement this function. So this is really easy to do. So we have to iterate. So let's see what we have to do. We have to iterate. First thing, we have to check if this is a square matrix. So to simplify the job, I'm gonna write a macro that does this for us. I don't think this will be used, but for now I'm just gonna put that here. So we define matrix is square, or just square. We probably have to, I will replace this with is, right? We definitely need to replace the rest here. So we have valid right? So we change all of occurrences and we just put s. So we ask the library if the matrix is valid or not. The same thing we apply with is square. And the only thing that returns is hold on. We have the matrix, right? M is the matrix. Then we simply have to return the condition. So M dot rows is equal to M dot columns. And it is like that, right?